perceptual metacognition and theories and models of conscious experience. And I think that's what she's going to tell us about today. So thank you, Megan, again for doing this, and thank you for literally just going straight from your bed to your desk. So over to you.
Thank you, Steve. That was really a very kind introduction. And again, I apologize for my tardiness. One of the things we've been working on recently is Neuromatch Academy, and so my schedule has been completely crazy. So I apologize for mixing up my time zones. I should be better by now. But in any event, I hear that you guys have had a fantastic summer school, and I wish that I could have come to more of it. And I hope that this talk will kind of bring together some of the things that you've been talking about with metacognition and consciousness. And the idea here is not to present totally empirical work, but to kind of present a theoretical framework where the idea is to identify the foundation that will allow us to link metacognition and consciousness and to actually tackle consciousness from a scientific perspective, instead of just from our armchairs and just through introspection alone. And I know that that's a very bold claim. And I also know that that's a very inflammatory claim, because there are lots of people who think that they're doing that already. And I agree that they are doing that already, but I think that we can always do better. And so I'm hoping that I will convince you of this argument today. Okay, so let's just get going. Okay, so first we'll start by saying that you presumably are conscious. And one of the things I'm sure that you guys have been talking about in this summer school is the something that it's likeness for consciousness, that there's something that it's like for you to feel your feelings, to see the light that's coming in through your eyes and hear the sound waves coming in through your ears right now. So the word that I'm going to use throughout this talk to describe this is not so much something that it's like, although I'll use that phrase, but I will also use the phrase phenomenal character, so that these perceptual and emotional and memory experiences have phenomenal character. And so, of course, as consciousness researchers, the idea, or the big question that we're asking us is, how does this happen? Not necessarily just why does it happen, because that's also an interesting question, but how is this feeling that has phenomenal character generated from neural activity? Why is this doing this? Okay. Okay, and so there are lots of potential ways that people have put forth to solve this so-called hard problem, Dave Chalmers' hard problem, as it were. And so, for example, we have global workspace theories, local recurrency theories, integrated information theory, quantum theories, higher order theories, and so on. And this is not meant to be an exhaustive list. The point of putting up all of these theories here is to highlight that all of these theories, or a lot of them, are at quite different stages of development. Some of them are very young, some of them are more mature. They also target different things. So some of them are really mathematical, but they're not as grounded in empirical data. And others are more philosophical, but may not have immediately obvious approaches for scientific inquiry, experiments that we can go and do. And so this plethora of information seems to suggest that maybe the hard problem isn't ready to be tackled by science yet. Now, Templeton World Charity Foundation would disagree with me. They've got a couple of these adversarial collaborations that they are funding to kind of pit two of these theories against each other and make them fight it out with empirical science. And there are more that may be coming along the way. But I think it's important for us to pay attention to and identify that these theories are really quite diverse in the types of questions that they ask. And so it's actually really hard to pit them against each other because they are often living at different levels of explanation. And so you might be asking yourself, well, okay, that sounds really pessimistic. Is it possible that consciousness can even be studied scientifically at all? Or should we just leave this to the very excellent philosophers and let them make progress on it, and then we'll pick it up again in several hundred years after they've kind of figured out some stuff? And I don't think the answer is that we should set this aside for now. I think the answer is that yes, we can study consciousness scientifically, but only if we start by tweaking the question a bit. So instead of asking the question, how do we become phenomenally aware? I want to change the question to how can we scientifically study how phenomenal awareness is generated? So this is more of a meta question. Instead of just asking the pure science question, we need to take a step back and say, okay, which scientific modes of inquiry, which scientific questions, which scientific approaches, and which toolkits and tools that are already developed for other stuff in science are going to be most appropriate and most promising for studying consciousness scientifically. Okay, and so this means that we're not going to focus on supporting or killing one theory or making one more attractive than the other, either theoretically or empirically. We're talking about the practical approaches, which types of approaches are going to be precise and falsifiable and allow us to, through these theories, make unique and quantitative predictions. Okay, so that's what I just said, is that we need to focus on the practical approaches and specifically identify approaches that will pick out precise, falsifiable, unique, and quantitative predictions. And so just as a case in point, I'm going to pick on IIT a little tiny bit here, but just to say that IIT says essentially qualitatively, more information equals more consciousness. And I don't think that there's a whole lot of people who would kind of disagree with that general idea. We also see this in empirical studies of metacognition, that higher performance equals higher confidence. Well, okay, that's still not very interesting and not very useful. And most people would agree with that, and most theories would agree with that. So we need to find the holes. We need to find the places where the theories bifurcate. Okay, and so that's what I just said. This one would be the same kind of idea for like global workspace theory, that more broadcast equals more consciousness, not particularly useful from, a unique falsifiable perspective. And so what I'm going to try to convince you of today is that I think that perceptual metacognition actually offers us the right toolkit to do this. That I think that gives us the precise and quantifiable predictions that we need in order to actually make progress here. Okay, and so I think you guys all kind of know what perceptual metacognition is, but I like to put up this slide because I think that it highlights, what we're talking about here. So this is you, this is your visual scene, and this is something that's up there ahead that you're driving along and you want to see what it is. And so your brain has to make a decision on the basis of the incoming noisy information about the identity of this object. And then it also has to make a decision, or what comes along with this decision is a feeling of confidence or uncertainty. So you get this feeling, this sense of uncertainty. And there are a lot of people actually, for example, Jan Drugovich and Alex Pouget, who talk about how the brain computes uncertainty. And they don't talk about how it comes along with a confidence judgment. But I think that here, that a feeling of confidence. My brain is not working yet. I'm still pre-coffee. But I think that if you think about this, you'll recognize that there is something that it's like to feel sure, and that this is quite a modal feeling. You feel like you can see, and that there's something that is shared between the feeling that you can see well, or that you're confident in your visual perceptions, and the feeling that you can hear well. It's kind of hard to put your finger on, but I really do think that there is something that it's like to feel sure. So this gives us a kind of reasonable target for that something that it's likeness in perceptual metacognition. And of course, this is something that not only humans and animals do, but it's something that eventually it will be important for us to build artificial systems that are capable of doing this, both so they make smarter decisions, but also so we can trust them better, so that we understand that they are making decisions based on uncertainty. And I know that Steve has a brilliant new initiative on this, and I'm looking forward to kind of seeing where that collaboration with AI researchers goes. Okay, so that I think is the introduction to why we can study metacognition. There's something that it's like to feel sure. It might give us a quantifiable kind of scientific framework. But I'll show you 3 specific reasons why I think we should study metacognition. And then I'll introduce what I'm calling the M-step approach, which is the metacognition as a step towards explaining phenomenology approach. It's the silly acronym, but there's a reason behind it. And then we'll do like a 30-second summary. First, why should we study metacognition in a little bit more detail? So not just we can do metacognition and there's something that it's like, but it also is objectively definable. And so what this means is I come from a computational modeling background. I did my PhD in multisensory integration and computational models of multisensory integration. And if you've studied multisensory integration or perceptual decision-making, you'll know that there is this like 70-year history, 80-year history, 90-year history of developing really beautiful, really precise models of how the external world relates to our internal type 1 decisions. So there's lots of math, lots of beautiful graphical models, lots of frameworks that compete, lots of ways of arbitrating these models quantitatively. And I think that this is really cool because it means that if we take all the power of all of those computational models that have been developed and refined and beautified over the decades for perceptual decision-making, and now we point them at metacognition, I think that that gives us a really powerful framework. And we've started to do that over the past 10 years, but I think this field is still really young. And we've got a lot of work to do, but it's also really exciting because there's a lot of work to do. There's a lot of space for folks like all of you to pick this up and to make some very real progress. So it's objectively definable. We've got objective computations. We can write down equations. This gives us precise predictions. That's cool. It also has what I'm calling hierarchically dependent anchors. And so what this means is that a metacognitive assessment, the result of that metacognitive process that we get in a confidence judgment, is about both external reality and the internal state of the system, the decision that you're making, and the relationship between the two. So when you make a metacognitive judgment, you're not just judging the outside world. Of course, that's a type 1 assessment. And if you really think about it, you're not just judging your type 1 representation and decision either. A lot of times we think about metacognition as being about an internal state. But if you think about what a confidence judgment is doing, it's about an internal state and the relationship between the internal state and the external world, and about the relationship between the decision-making process that you had to make the type 1 state and the decision-making process that you had to make the type 2 state. So it's this crazy complicated interdependent thing. And what's great about this is that means that the system has a lot of hidden moving parts, and it's really hard to fit it. And we like models that are hard to fit, because that means that if you twist your experiment into a crazy mess and you get your model to fit the data that your person or your model animal produces, there's a better chance that that model is right, because it's much easier for it to break. It's much easier for it to make the wrong predictions if it's trying to fit a really complex system. So together, I think that that metacognition, or the result of metacognition being objectively definable, confidence judgments are things that we can write down equations to get to, and the fact that the system that we are working on is hierarchically dependent, together, I think this makes this a really promising and powerful framework. We've got a system that's really hard to fit, and we've got a bunch of really beautiful, refined, and mature tools that we can use to fit it. And so this gives us that sensitivity and specificity that I was talking about earlier. And just to give you a graphical representation of what this is going to look like, so this is kind of a standard graphical model. We've got a stimulus, we've got an internal response variable that we operate on. We apply a decision policy of some kind, and we get an estimate. So this is like an internal probability distribution. This is an estimate. And then you have some other kind of process. So I'm saying that these are, X is a function of S, and Y, which is the type 2 judgment, is a function of X. And then there's a decision policy here. And then there's all these other variables in here too that may also go into both the type 1 and the type 2 judgment. And so I'm calling these theta and lambda just for the sake of argument. This is just to say there is stuff outside the stimulus that might affect your decision. And there is stuff outside the decision that might affect your confidence judgment that may include the same stuff that affected your decision, or maybe it doesn't. And that's all I'm saying here. And so what I wanted to do in creating this figure, which is by no means complete, and I'm sure that there are lots of feedback arrows and all sorts of stuff that I'm missing, is to highlight the different levels at which we can study the system. We could pick out just the decision policy by itself and study that, or just this decision policy by itself and study that. We could pick out just this functional form or just this input and so on. But right now, as I'll talk about, a lot of the studies that we're doing are like, I varied some stuff about the stimulus, or I varied one of these things and I saw a difference here. And like, you don't know what you messed with. You could have messed with this, you could have messed with this. You have no idea what you actually like touched in your experiment. So I think that we need to be aware of the complexity of the system, and also the ways that each of these pieces, decision policies, functional forms, interdependence between functional forms, all sorts of stuff, these have all been studied in perceptual decision making. So we should pay attention to those older papers and look at how they hold everything else constant, but they just vary the decision policy, and they look at how it fits the data differently. Okay, and then of course, the third reason that metacognition is cool is that it's subjective, which we went over earlier, which is that there is something that it's like to feel sure. And so we can at least make the argument or the claim that we aren't just studying metacognition, that by doing this, we will actually get at something that has to do with how one type of phenomenal experience or experience with phenomenal character, one type is generated. Okay. So, okay, these are our three properties that I think make metacognition a really strong and appealing and attractive target for those of us who want to study consciousness. That it does have that phenomenal character, but then it also has these really attractive and really powerful practical properties, which is that confidence is objectively definable, and that we have this super complex system that we are trying to fit. Okay, and so this leads me to the claim that by studying metacognition, we can actually get unprecedented precision of inquiry into at least one type of phenomenology. And as you'll see later, I'm not going to make the claim that this might solve the hard problem of consciousness. I don't have that much hubris. But I think that at least this is one type of phenomenology that we can tackle, and that might open the doors or at least show us the way to tackling others. And also because of property 3, which is those hierarchically dependent anchors, this precision is unavailable for type 1 models alone. It's much easier to get a model to fit type 1 behavior than it is to get it to fit both type 1 and type 2 behavior. So it's much easier to break a model of metacognition than a model of perception, and that's good from a modeling standpoint. And so this is what I'm calling that metacognition as a step towards explaining phenomenology approach in the grand tradition of sticking M on the front of things and making them related to metacognition. Okay, so let's just go quickly through what this means and how we would actually do that, because the focus of this talk is practical. Where we want to make progress so that we can actually tackle this topic scientifically. So I'll do a brief primer on computational models just to get us all on the same page. For many of you, this is going to be really elementary, but I think it's good to put it in cartoons and really show it that way. So for any model that we're building, we have a model, and that model makes predictions. And so this could be as simple as, I think that I draw a sample from a normal distribution and I apply a decision threshold, and that's signal detection theory. So this could be as simple as that I have like these two normal distributions. I draw a sample from one of them and I categorize it based on a threshold. That's a model. And so the idea then is that we have these models and they make predictions about behavior, both decisions, type 1 decisions, and type 2 judgments or metacognitive judgments, or any other model. I mean, this could be a model about like climate data or the stock market or anything. It's going to make predictions, and then you have empirical data, and the goal is that you want to fit your empirical data and your model together. You want to fiddle with your model and its parameters, and then measure how well it predicts the data based on a measure of goodness of fit. And so to take this down even further, this would be like an R-squared measure in a regression. A regression is a model that you have empirical data, you get an R-squared. How well does the line fit the data? And so in models of perceptual decision-making and confidence judgments too, a lot of times the goodness of fit is measured with a likelihood function like this. This is the likelihood of the model parameters given the empirical data that you have. And this is a product across all stimuli and response types, IJ, of the probability of that response given that stimulus from the model. So I've color coded this so that it goes with the model. And then you raise that to the power of the number of responses to that stimulus type, responses of a given type to that stimulus type that you get out of your empirical data. So again, this is color coded. And the idea here is that this quantity gets bigger if the green and the blue match, and this quantity gets smaller if the green and the blue don't match. Okay, so by this, you can actually fiddle around with the parameters in your model. Let's say you have a y equals mx plus b kind of model. You fiddle around with m, you fiddle around with b until you maximize the likelihood of those model parameters taking on a specific value given the data that you have. So ideally, your likelihood function looks something like this. Where you have this non-monotonic function that is nice and beautiful and smooth, and it has a peak, and you say, aha, these are the best fitting parameter values for my model. And if I change the parameter values over here, I get a not so great model. So that's not, a good fit to the data. And you'd say, okay, fantastic. I've optimized my model parameters. I have a beautiful model. It predicts my data. It does a good job. This is great. I win. I've solved the scientific problem that I'm trying to solve. And then you forgot that, well, there maybe is a whole other model out there that's just totally better fitting in general. And so through comparing the likelihood of the model with its best fitting parameters here and here across models, and then you also penalize for number of model parameters. So you penalize for model complexity. You can then do these model comparisons and say, aha, so the purple model is actually a better description. And under the hood, then I can say that this set of equations and this set of interdependencies is the better description for how the system is actually producing these confidence judgments. Okay, and you're thinking, okay, well, great, I took statistics, guys, like I'm good. Why do we need to do this for metacognition again? And isn't this just the standard model fitting that you learn about in your undergraduate statistics classes? And the answer is yes, except remember this thing. So to get that beautiful, nice likelihood curve and to get the model parameters that are optimal for your data, look at all the stuff you have to specify. You have to specify not only the input, so you have access to this, you're the experimenter. In experiment world, you are God, you can control this, but there's not a lot of other stuff you can control, so you better go measure it. And then you have to make guesses about all of the colored things, all of the decision policies leading from the internal distribution of X given to give you X hat, Y to Y hat, and these functional forms here. You have to make guesses about all of those. And if you don't guess right about this one, but you did guess right about this one, you might not see that you got it right because the definition of this depends on this. So this is really hard. But if we can do formal model fitting with this, then we might actually get somewhere. And so this is the idea here, is that we will try to formally fit this system to the extent that we can, and we will have a system that's easier to break. And just to show you really very specifically what this looks like, if you just take the bottom half of this system, a stimulus to an internal response distribution, and then like a decision policy and a response on it, then in a 2 alternative forced choice experiment, here's a thing, is it a face or a house? You will get response distributions that look like this. And in a 3 alternative forced choice experiment, is this a face, a house, or a chair? Then you'll get a response distribution that looks like this, where the stimulus had a particular identity and the observer said a particular response. If you add type, this should say type 2 anchors, sorry. If you add type 2 into the mix, now suddenly you have a much more complex response distribution. And not only are there more pieces, this is a more nuanced distribution, but you'll notice that these are hierarchically dependent. If you said this, you really can't say this. So there's a lot of ways that this distribution will express very different shapes and different dynamics over time, over learning, and so on, than you would get out of the type 1 systems alone. And so this is the type of system that we're trying to fit with that likelihood function that I wrote out earlier. And so just very quickly, I wanted to show you some of the ways that we've been doing this over the past few years, starting when I was a postdoc with Hakwon Lau, is when I took all those computational models that I built of multisensory integration, and I pointed them at metacognition and consciousness. And so I'll go through 2 of these in a little bit more detail. 4 of these in a little bit more detail, just very quickly, like 1 or 2 slides each. I think I mentioned this paper, and I hope that a couple of you got a chance to read this one. But the idea in this study is that we wanted to understand blind sight, which is when you can do a task, but you report no consciousness about the stimuli that you're doing the task about. This here is a representation, a graphical representation of the type of model that we've been building. And this little figure is going to come back over and over throughout the talk here. So the idea here is that you have a system of generating distributions. These concentric circles are meant to be 2-dimensional Gaussian distributions, kind of as viewed from above. So they're little hills of probability. And you draw a sample from one of these distributions, and you categorize this sample on the basis of the posterior probability of right or left. So you draw this sample, and then you basically compare it to this generating distribution versus this one. And you say, which of the 2 generating distributions is it closer to mathematically? And then you pick that one. You say, okay, this is probably most likely a left tilted Gabor patch instead of a right tilted Gabor patch. And then what we did in this model is we drew a second sample from just the noise distribution, and we categorized that. And then we compared the posterior probability of these 2 samples, of the choice that was made for these 2 samples, and we called that the confidence judgment. And so in the paradigm, what people are doing is they're presented with a left or a right tilted Gabor patch that's forward backward mass. So it just blinks onto the screen very quickly. And then they're presented with nothing, which is this sample, which blinks onto the screen very quickly, just a nothingness. And these are all counterbalanced. And then they're asked, which of these 2 things are you going to bet on? So they have to categorize, is it left or right tilt? Is it left or right tilt? And then which one will you bet on? And so this model exactly replicates the task that the people are trying to do. And now we have a quantitative guess at how this hierarchical system works. We have a sample, we make a decision, and then the confidence that goes with that decision is simply a readout of the posterior probability of the choice that you made. This is a very, very standard model for confidence judgments. In fact, this is probably the one that everyone says is, oh, that's just totally what people are doing for confidence, right? Wrong. You'll see why. So these are the predictions for what the model behavior ought to look like. So as orientation percent correct increases, so as the contrast of the target increases when the target is there, so the task gets easier and easier and easier, you get better at the task. That is not surprising. And you also have increased ability to bet on your target present interval. And by you, I mean the model. So this means that as the model gets better at categorizing left versus right, it also gets better at telling which interval has the thing in it. And so if you're wondering why this dips down below this identity line here, it's because this x-axis is based on a judgment just in the target present interval, and the y-axis is based on a comparison between judgments made in both of the intervals. So there's 2 noise sources in that y-axis here. So these are our model predictions from our ideal observer, and As a reminder, this is what the distributions would look like if we didn't have the confidence judgment, the red part here. It would just be make a judgment about this thing, make a judgment about this thing. And that's all that I would have available to me to fit my model. With metacognition, I get a lot more response profile to fit. And so it's going to be much harder to fit my model, much easier to break my model. And also these are not independent. Type 1 and type 2 judgments are dependent, as I showed you earlier. So these are the predictions from the ideal observer. And then we compared this to a blind sight-like observer that kind of captured folk psychology expectations about how it is possible to do a task above chance, but have no ability to bet on your judgments or no ability to kind of see the target that's out there. And remember, I mentioned that it's difficult for models to fit a metacognitive task. It's easy to break them. Well, it turns out that in a bunch of experiments, we didn't break the model, that the human behavior actually looked an awful lot like the ideal observer. It looked a lot more like the ideal observer than it did like this blind sight observer. So we concluded that maybe it looks like humans are ideal observers. In these experiments, and that will come back to haunt us later, but we also can conclude at the meta-science level that we can capture, we can model and quantify one guess at the computations that underlie metacognition in this type of task. Okay, and so then we said, okay, well, we better make sure that this is true. We did a bunch of experiments, but none of them actually manipulated the brain activity. So previously it's been shown that transcranial magnetic stimulation to various spots on your head can mess with metacognition in various different ways. Steve's got a great paper where they zap you in your motor or premotor cortex, and that messes up metacognition, but doesn't mess up your decision making. You can also apparently zap DLPFC, and it does a similar thing. And if you zap primary visual cortex here on the back of your head, you can mess up both. So you can reduce their capacity to do the task because you're injecting a huge amount of noise into your brain. But in doing so, you also reduce your awareness of the target. And it has been reported that you can do this in a way that reduces the awareness of the target more than it reduces the performance itself. And so TMS to early visual cortex can create something that looks like blind sight. Well, you can still do the task just a little bit, but you have no ability to see, or you report no ability to see the target. So we do the same thing, same exact experiment where we show you a target and we zap you in visual cortex, and we show you no target and we don't zap you. But we also counterbalanced all this stuff so you didn't catch on to any interdependencies between zapping and target presence. And then we said, which of these two things are you going to bet on? And so the trials that we're interested in looking at are those where there was a target present and we zapped you, because these are supposed to create blind sight. These are supposed to create conditions where you can do the task above chance, but you have no ability to bet on your choices or see the target at all. And so now we compared this to the ideal observer model, and ta-da, it broke, and it broke spectacularly. So here, red is the people and black is the model, and you can see they don't match at all. So yes, as as performance increases, confidence increases in both cases, but these lines are parallel and very far away from each other. They're not overlapping. And this is with the best fitting parameters that we can find. So what's going on here is that the model predicts that as you inject noise into the system, you reduce performance and you reduce confidence. And that's what's also kind of been reported before in a different experimental paradigm. And what people did was they reduced their performance in the presence of TMS, and they increased their confidence. They bet on that thing more, not less. And so this is consistent with actually some other work that was conflicting that was published by Dobie Ranov back in 2012, 2014, something like that. So 2012. So the idea here is that now we have to change our model. We have to add an element that says, okay, this ideal observer is wrong. This is not what the system is doing. What could the system possibly be doing instead? And so now we get into our model comparisons. So we built what we called a heuristic observer. And the only difference between these observers is that the ideal observer knows that the noise got bigger. So we allow the ideal observer to obtain an estimate of its own noise. So once we inject noise into the system, this observer is allowed to recalculate the covariance of the internal response distribution. And this one is not. That's the only difference between the observers. But look, the heuristic observer actually does a great job. So this suggests that humans are maybe suboptimal somehow in their metacognitive assessments, which is consistent with a lot of previous work, but it resolves an apparent conflict where some people said TMS could cause blind sight and other people said, no, TMS increases confidence. This shows maybe what's going on there, that there is maybe a response bias at play. And so these formal model comparisons then reveal how people can have suboptimal metacognition, and that we can write down the math for it. So just really quickly, I'll show you that we've done this a couple other ways. This is an ECOG study. We showed people faces and houses, and we did some decoding of the responses from recordings directly on the cortical surface. And we pass the information that we kind of extract from the brain through the decoders. We pass that into various of these kind of models. I told you these would come back again. And now we have this model was actually the winner in our exceedance probability model comparisons. So this one was kind of saying, once you've made a decision, all you care about in rating your confidence is how much evidence you have favoring that decision. Never mind how much evidence you have opposing the other decision. And then, so given that this is the winning model, we've been working recently with Brian Maniscalco to develop something that looks a little bit more biologically plausible, so that we can say what kind of neural circuitry might be involved in actually implementing computations that look like this, so that then if this model is the winning model, and if it is implemented this way, then we can go looking in the brain and seeing if we can find, evidence for this using neuroimaging techniques. So it's a lot of ifs, but so far, this was the winner in a couple experiments, and this model fits the data better than anything else we found. And so we're hoping that the MRI experiments will be fruitful. And so then the last couple things that I'll show you before we wrap up are just two other studies, which is the previous studies that I just showed you kind of try to tackle this whole chain at once. And they don't really control for these other things, and they don't separate out study of this functional form from this decision policy and so on. And so I'm not really following my own advice, although in my defense, some of those studies are older before I developed this argument. But what we really want to do, and what I hope that you're starting to see, is we really want to cut this system. We really want to clamp the bottom half so that we don't have to mess with it. We don't have to worry about whether we got this right or whether we got this right as its input to this, or whether we got the decision policy right here. If we can just clamp this entire bottom of the system, then we can focus on the top half. And that makes our lives a lot easier, and makes our model comparisons potentially even more precise, and that the data won't get so buried in noise. So we've been trying to develop some techniques that will allow us to do that in experimental settings. So this is work again with Brian Maniscalco and Olenka. And Olenka was an undergraduate when she did this work, and now she's joined my group as a PhD student. So the idea here is that we're trying to isolate confidence. We're trying to cut off the bottom half of that entire causal chain. And so we're trying to create something that we're calling a meta-perceptual function, where instead of, so the idea is you hold D prime or performance constant, and then you find ways to push around on confidence. And so that'll allow you to mess with the top half of that causal chain while leaving the entire bottom half exactly the same. You could maybe do this at a couple different levels of D prime. And this is in fact what has been done in the past, is that you find like 2 levels of performance and you mess with the stimulus in a way that you can kind of manipulate confidence independently of performance. But what does this whole function look like? Does it actually come together at the bottom here? Or are these like totally parallel all the way through? Do they look like psychometric functions in terms of like that kind of S curve shape, or are they lines? We don't know. But if we could find out, then we wouldn't have to worry about matching performance anymore. We would be able to just look at the entire response distribution of D prime versus confidence, And we wouldn't have to worry about relying on a null statistical test saying, oh, performance was not statistically different in these two conditions. Instead, we just have the entire response distribution of D prime versus confidence. So this is what we're calling the meta-perceptual function, or a type 2 psychometric function, which relates perceptual decision-making to meta-awareness instead of your standard type 1 psychometric function, which relates the stimulus that's out there in the world to your perceptual assessment. So how do we measure this whole function in a way that actually just doesn't have D prime and confidence covary? So this is the paradigm that we've been using. The idea is that these are random dot kinematograms. This looks a little bit like a snowstorm on your computer screen. And then for a brief period that's about a half a second long, in one of these two circles, which are not outlined on the screen, they're just there. The circles are there just for illustration. The snowstorm briefly is coherent in a downward direction on one side or the other. And then it goes back to totally random. And we do this in 3 different densities of dots, or 3 different levels of intensity of the snowstorm. So we go from flurries to blizzard, basically. So we're manipulating the amount of dots and the density of dots that's on the screen, but meanwhile, we're also manipulating the coherence of the downward dots when they do show up. So either this is like 100% coherent, 100% of the dots in that little circle move downward. That's a very easy trial. Or like 5% of the dots in that little circle move downward. And that's a very difficult trial. So we manipulate the density of the dots, and we manipulate the coherence of the coherent motion of the dots. And we do this either in a blocked design, or we completely interleave all the trials. So here the snowstorm is varying across time, and here it's like now it is a blizzard, and now it is flurries, and now it is in between. And so we take this and we plot that D prime versus confidence curve. And in the blocked condition, which is this one on the left, you can see that the curves actually don't come apart. So if we were trying to do it in a block design and conclude that we've actually matched performance but created different confidence, it's likely due to a statistical error if we did it in a blocked design. However, the interleave design looks really promising. We can see this very clear separation, especially at higher D prime values. So this shows us, don't do this at threshold. Do this actually way up here if you want to find cases where D prime and confidence come apart. And that in the bottom, they tend to kind of collapse into nothing, which makes sense, that if you have no D prime, your confidence isn't going to change a lot. But it could have been a response bias. It could have been actually something that changed down there too. So now what we're working on is ways, so this is the empirical result, that this is a bigger effect than this. At higher D prime, the effect is bigger. And so this means that this is characterized as a horizontal, not a vertical shift in these meta-perceptual functions. So now we're working on ways to characterize this function a little bit more cleanly, to understand its functional form, and to maybe, I hope, create a little toolbox so that people can actually fit these things and do these analyses for themselves in their own experiments. Okay, and then the last experiment that I'll tell you about is again a case where performance and confidence come apart, because I think these are the best way to do this. And so
probably if we have about 3 more minutes, is that okay? And then we have time for questions.
Yeah. So I'll just very briefly introduce this, and I won't go through the details of the modeling. So the idea here is that there's this interesting phenomenon where in the center of your visual field, we have better spatial acuity, and we generally have higher confidence. And in the periphery of our visual field, we have poorer spatial acuity, and we generally have lower confidence. But a weird thing happens in that you feel like you can see pretty well in your visual periphery. The experience that you have of the world looks like this and not like this. And so this is a great opportunity to isolate confidence by using natural scene statistics. So the idea here is that maybe the system has become sensitive to the natural statistics of its environment, not about light location or orientation distributions in natural scenes, but in noise. So the system has learned that the center of the visual field has lower noise and the peripheral of the visual field has higher noise. And it uses those expectations of noise as an empirical prior to then estimate noise online. And so we suppose that this is what people are doing, but then we made an additional assumption that maybe the system has not learned this empirical prior perfectly. So the empirical prior in the visual periphery is that noise is bigger and is probably positively skewed because, hey, noise can't be negative. So this distribution probably has a positive skew, but maybe the system doesn't know that. Maybe the system has learned that the noise in the visual periphery is bigger, but it doesn't know it's positively skewed. So in this set of experiments, we asked, was that one mistake enough to explain this experience of peripheral inflation? So I won't go through the details of the model for the sake of time, but we built a whole bunch of models and we did a whole bunch of model experiment comparisons. And the take-home message here is that models that are blind or estimate confidence imperfectly, or estimate, in this case, noise imperfectly, they go through a hierarchical inference process that uses the wrong prior. They create peripheral inflation, and the models that are ideal observers in noise estimation don't. And then the last thing is that you can push around on this effect with attention. So you can create conditions where in unattended trials, you have poorer performance, but higher confidence in your incorrect trials, and nothing changes in confidence in the correct trials. So this is the empirical result. And so then we did a bunch of simulations with all those models that I showed you, and I'll just orient you briefly. The red line being completely flat along here means that confidence in correct trials did not change no matter what we did to this model. But confidence in incorrect trials was always bigger in unattended than attended. So this line being consistently negative. You'll notice model 5 is the only one that shows this pattern. So that's the winning model. We can talk about the details later if you want. Sorry, I'm running over time. And so this shows how maybe we estimate noise in our own predictions. Okay, so lastly, what do we get out of this for consciousness? And I know I'm running out of time, so I will just go very quickly. We get the ability to factorize the inputs here to confidence. We get the ability to explore the functional form of this separately. We get the ability to characterize the distribution of Y. What dimensions does it have? We get the ability to study the decision policy separately. And we get the ability to think about closing the loop and talking about feedback, because we can build that into our models. We can build temporal dependence in and make this thing more complicated. And so just to summarize, I think that this is an ability, this gives us an ability to study consciousness empirically, because it'll allow us to get a handle on one type of phenomenal experience, which is the feeling of confidence. We've got a lot of models that have been built for this, which I showed you, but we have a lot more work to do. And so I think that this is what we need to do, is that metacognition is going to help us build models of generative, that are generative explanations of how phenomenal experience is generated, because we will get a mathematical handle on that. And so lastly, I will just plug this. We've got a lot of work to do. If you are in the United States or planning on coming to the United States, you can apply for this workshop. And but the idea is that we're giving away sub-awards. So it's not just come to the workshop. It's that we want to give you money to do really cool experiments. And this is a generous funding by the Templeton Foundation, World Charity Foundation. Okay, now I'm going to stop. Sorry, I ran over time. Thanks.
That was totally wonderful, Megan. Thank you so much for a fantastic talk. And you drew together so many strands of what we've been talking about over the past 3 days. And I think it really highlighted how, you know, there is so much work to do, which is fantastic for, you know, everyone to hear. And also the devil is in the detail. You know, the models matter and specific empirical findings matter, and, you know, really showing a roadmap to being able to do serious work in consciousness science and metacognition. So thank you so much for that. Also incredibly impressive to do so 45 minutes before you were meant to do so. So
that was my fault. That was my fault.
So yeah, so please do put questions in the Q&A. We have 10 minutes or so for questions and discussion. Maybe while people are doing that, I'm sure there are some. I can just kick off. So what we were doing earlier in the day was we had a live tutorial exercise going through computing meta D prime, looking at confidence rating data, fitting models to those data. And I'm just wondering whether you can unpack for us a bit, how does the meta-perceptual function relate to those ideas of metacognitive bias and sensitivity? So we covered a lot of that this morning. I'm just wondering, for everyone here, you could just unpack a bit, like what additional insights can the meta-perceptual function give you that those measures can't? How could we be using this?
Yeah, that's a great question. So I think the meta-perceptual function really targets it targets metacognitive bias much more than it targets metacognitive sensitivity. So it's about how your overall confidence judgments change as a function of different stimulus manipulations that we're going to do. One could build, I suppose, something that looks a little bit like the meta-perceptual function for metacognitive sensitivity, but that's kind of what's been done before, in that we have different conditions where you put D prime on the x-axis and you put meta D prime on the y-axis, and you kind of look at what's happening to meta D prime as a function of D prime. I think that it would be interesting to see how those interact. So one could, in fact, calculate meta D prime in all of the conditions that we have. So we have those data. I suppose we could go do this. And that might be interesting to look at. The paper was under review and came back, and we needed to make, we saw the opportunity to make it into a toolbox and everything. So we actually kind of like pulled it and decided to do a lot more work on it before we sent it back out the door. So the preprint is there, but it's going to be, I hope, quite different when it really comes out. So we could go do that and see what the metacognitive sensitivity is. But I think, in answer to your question directly, this is trying to understand cases where your confidence judgments vary independently of your overall perceptual performance capacity. And this is based on the observation, 15, 20 years ago, that because confidence and accuracy co-vary, you can't just measure confidence alone. You have, and if your performance changes, you can't just assume that the confidence changing like concomitantly is meaningful or interesting. You have to actually like measure, did confidence change to the exact extent you expected it to under the conditions of the perceptual decision-making capacity change that you observed? And you can't do that without models. Because you can't write down what you expect to happen to confidence without the model. So I think that fitting meta D prime and fitting, I don't know if you did metacognitive bias in some of your,
much, but yeah.
Yeah. So I think that all of these are really important to doing these model arbitrations, because if you write down a model and it gets the metacognitive bias right, but it crashes and burns for the metacognitive sensitivity, then that's not the right model either. And that's actually been a really powerful tool for arbitrating some of these models, as we've discovered. So the paper that Brian Maniscalco and I just published a few months ago, meta D prime was the key. Metacognitive bias alone was not the key to the model arbitration. Metacognitive sensitivity was the one that allowed us to say that model just crashes and burns. It just cannot get it right. The only one that worked was the only way we could arbitrate them was based on metacognitive sensitivity.
So there's a question in the chat from Cormac. He says, great talk. Wondering how you conceive the link between feelings of confidence and other affective states like anger, happiness, etc.
Yeah, this is a great question. So I go into this a little tiny bit in the preprint, but I don't expect any of you to read it because it's like 60 pages long. so it's a challenge to fit that into, a talk like this too. But I do talk about this just a tiny bit, more in the broad sense, which is the feeling of confidence relative to other subjective feelings, like the feeling of anger, happiness, the feeling of brightness, the feeling of pain, any of these things. So I think that there are different kind of strengths of the argument that I'm trying to put forth.
which are, if you agree that there is something that it's like to feel confident, that confidence has phenomenal character, then if we build these models, we can understand a little bit more about how that type of phenomenal experience is generated. Now, does that actually translate to all other types of phenomenal experience? Or are there categories of phenomenal experience that this allows access to that, and others that still remain completely opaque based on like the similarity of that phenomenal experience or the category of that phenomenal experience relative to confidence? So I think the strong form of what I'm trying to say is, if we can write down the equations to get at the feeling of confidence, then we will learn something fundamental about how we create a substrate that phenomenal experiences can like live in or rest on. And so that version of the answer to your question would be, well, we get at anger and happiness and other subjective states too by studying this. I'm not sure I really espouse the super strong form. I think I'm more on the intermediate or weak form, which is this is perceptual awareness, perceptual phenomenal character. And so that if we can build these models, then we will get at how perceptual experiences are generated, and that might give us like pointers to how to understand emotional experiences or other phenomenal experiences, but I don't think it's going to be an obvious, like just kind of come out in the wash type of thing. Yeah, so that's my answer here, is that I don't study emotions. And so I'm going to conveniently slip that one under the rug, but I do think that getting a handle on a phenomenal experience will at least point us in the right direction for some of these others, I hope.
So maybe I can ask you one more question. So it relates to something I mentioned. So in my talk this morning, I mentioned briefly the positive evidence bias. I also put up that figure from Koizumi. And this is something we've been wondering about too, but you've done lots of beautiful modeling work on why, trying to explain why confidence inherits this kind of detection-like effects. Like the positive evidence seems to contribute more to confidence than it does to accuracy. But I'm just wondering, like more broadly, and maybe this relates to the relationship to phenomenology or consciousness. Why is that set up like that? Why should it be the case that is the case? And does it tell us anything about awareness?
I think this relates to some of the work you've been doing, Steve, in your higher order state space model too, is this that perceptual decisions that we ask people to do in the lab are quite artificial. It's like, here's a thing that's definitely there. What is it? Or here's a thing that may or may not be there. Don't care what it is it there or not? So these are discrimination and detection tasks. And like, no, we don't do this in the real world. We're constantly doing both, which is what your model does. It's that it decides, is there a thing there? And then if there is a thing there, what is it? And then we kind of operate on it in that way. And I think if you write down either the sets of models that you've been using that kind of have that hierarchical approach, but even in a flatter model, that if you assume that what the system is doing is in that two-dimensional framework where you have like, leftness and rightness and nothingness, usually we say, okay, this is the decision axis for left versus right, and I'm going to integrate out, or I'm going to marginalize over the strength of evidence. Or because I don't actually know the strength of the evidence that was presented to me. So I'm just going to marginalize over that nuisance variable and get rid of it and ignore it. And just focus on the task relevant variable, which is leftness versus rightness. I think that's a mistake. I think that there are loads of other ways that we can write down this system. The first is kind of akin to your hierarchical model, and it's we buried it in Appendix 5 of that 2015 eLife paper, which is that the system first estimates how much evidence there is for each piece independently, and then uses that to do its confidence judgment. Another alternative would be to just put the likelihood of the data given noise in the denominator of Bayes' rule. And that would also give you something that looks a little bit detection-like. And I think that these are ways that we can mathematically explore how the system might be using strength of evidence, I think it's probably not so simplistic as we put it. It's not either or. It's not just detectability or just discriminability. It's some complicated combination of both. And I think we need to make our models more complicated there. But it also kind of speaks to maybe what the system is doing in general, that we can't write down a simplistic model that's just discrimination and have it fit the data. And people say, oh, well, this seems suboptimal. This seems like the system is not maximizing its reward under these conditions of this task. And I think the answer there is, I think we got the cost function wrong. It's not that the system is suboptimal, it's that it's optimal, but it's doing something that we don't know about. And we need to go figure out what that thing is that it's doing. Mm-hmm. So that would be my answer there, is that I think that the positive evidence bias is not a bias at all. It's a near optimal, or at the very least, adaptive solution to a set of really complicated constraints that an organism deals with. Mm-hmm. And so we shouldn't say it's a bias, maybe we should just say it reveals how the system is working, and we should pay attention to that.
Great. So we have one more question. I think we'll have to make this the last one because we're running slightly late in the chat. So Patchy says, yeah, this is an interesting question about whether you can have feelings of confidence without visual phenomenology, and i.e. blindsight patients. Yeah.
This is a great question, and it's one that I really I enjoy answering, because I don't feel quite satisfied in my answer. So every time I get this question, I try to work through it a little bit more. I think the answer is that it's kind of like what Ian Phillips has been exploring recently, in that we may not have any visual phenomenology, but that doesn't mean that there is nothing that it's like. So Ian calls this, what is it, like qualitatively different experience, in that you may not have visual phenomenological experience or phenomenal character that you would label as visual in its qualitative nature of the thing that's out there in the world, if you're a blindsight patient or ITMSD or something like that. But nevertheless, that doesn't mean that I've completely turned off any subjective experience that you have about the decision. So there's still something that it's like. It's just, if you imagine, and I'm still working through this, but I think that if you imagine the quality space, Rosenthal's quality space, as having dimensions that can be modal and dimensions that can be amodal. So you can have, like, this is how much, this is the visualness dimension, and this is the auditoriness dimension, and this is the confidence dimension, and this is the fuzziness dimension. I don't know. So you could imagine a case where the representation that you have loses one of those dimensions. The coordinate along that dimension goes to 0, but that still doesn't mean that there's nothing that it's like in general. And so I think that something like that is the explanation that I'm favoring, is that there's still a feeling that goes along with it. It just lacks vision in its labeling. And I don't know whether that's the case. And I'm not sure that all the dimensions are linked to the same receptor. I think that all the dimensions are linked to all the receptors and all of the computations and all of the other things that go into it. And so I don't know that it's all just vision in general. I think that when you ask someone about confidence, this is an answer to Patrick's question in the chat. When you ask someone about confidence, they're reporting something that is a combination of the feeling of confidence and the feeling of visual clarity and the feeling of something else and the feeling of alertness and arousal and all of these things. And so what we get out of a report of confidence and a feeling of confidence is a combination of all that stuff, I think.
There's an interesting, what you were saying seemed to remind me a lot of the interesting case of the patients who've lost large fiber somatosensation. So they don't feel their bodies. If you touch them, they don't know that you're touching them. But the more skilled ones are able to do quite a lot, and they report, well, I don't quite know what there is, but there's something. And it seems very likely that what they're doing is using residual small fiber thermal and nociceptive systems to get feelings which allow them to answer questions about tactile stimuli. So I guess what I was looking for is that these amodal dimensions that you were talking about, I mean, are they really going to be amodal, or are they just going to be using deviant receptors? I think that was the force of what I was interested in.
I would be happy with either of those scenarios. That I think that the mapping between receptors and dimensions of this quality space is as yet completely unexplored. And that would be really interesting to explore. And I know that there are some people, like now Tsuchiya is looking at kind of how information similarity and quality, report similarity go together. And I know Hakon's been talking about this too. And I think that this is the kind of the direction we need to go, but we need to do it in the context of like, how does that quality space get generated too? What are the inputs that actually matter? Not just let's look at what space of what I'm calling Y up at the very top. We can't just look at that. We do need to look at what goes into it a little bit. But I agree with you. Yeah, maybe it's that we don't have a single dimension for feelings of my body. Maybe that's also multidimensional. And so we've lost like a primary one of them, but there's still some that I don't know. I have no idea. This is like all very much, we've got a lot of work to do.
Well, Megan, this has been fantastic. You've managed to bring together so many threads that we've had over the past 3 days. So we should thank you again for a wonderful talk. Thank you so much. And
thank you for having me. And I am so sorry again for my tardiness.
No, well, hopefully now, you've got all this free time and you can go and have